Indeed, specifying the costs and benefits may take a great deal of time and thought. In many cases, they cannot be specified exactly, but only as approximate ranges. Chapter 8 will return to address what we might do when these values are not known exactly. For example, in our churn problem, how much is it really worth to us to retain a customer? The value depends on future cell phone usage and probably varies a great deal between customers. It may be that data on customers' prior usage can be helpful in this estimation. In many cases, average estimated costs and benefits are used rather than individual specific costs and benefits for simplicity of problem formulation and calculation. Therefore, we will ignore customer-specific cost-benefit calculations for the rest of our example, but we'll return to it in Chapter 11. Note: mathematically, there is no difference between a cost and a benefit except for the sign. For simplicity, from this point on, we will express all values as benefits, with costs being negative benefits. So, let's return to our targeted marketing example. What are the costs and benefits? For simplicity, all numbers will be expressed as dollars. A false positive occurs when we classify a consumer as a likely responder and therefore target her, but she does not respond. We've said that the cost of preparing and mailing the marketing materials is a fixed cost of $1 per consumer. The benefit in this case is negative $1. A false negative is a consumer who was predicted not to be a likely responder, so was not offered the product, but would have bought it if offered. In this case, no money was spent and nothing was gained, so the benefit is $0. A true positive is a consumer who is offered the product and buys it. The benefit in this case is the profit from the revenue, $200, minus the product-related costs, $100, and the mailing costs, $1. So the benefit is $99. A true negative is a consumer who was not offered a deal and who would not have bought it even if it had been offered. The benefit in this case is $0. No profit, but no cost. These cost-benefit estimations can be summarized in a 2x2 cost-benefit matrix whose rows and columns are the same as for our confusion matrix, which is exactly what we'll need to compute the overall expected value for the classification model. Given a matrix of costs and benefits, these are multiplied cell-wise against the matrix of probabilities, then summed into a final value representing the total expected profit. The result is that the expected benefit is equal to the probability of a true positive times the benefit of a true positive, plus the probability of a false positive times the benefit of a false positive, plus the probability of a true negative times the benefit of a true negative, plus the probability of a false negative times the benefit of a false negative. Using this equation, we can now compute and compare the expected profits for various models and other targeting strategies. All we need is to be able to compute the confusion matrices over a set of test instances and to generate the cost-benefit matrix. This equation is sufficient for comparing classifiers, but let's continue along this path a little further, because an alternative calculation of this equation is often used in practice. This alternative view is closely related to some techniques used to visualize classifier performance. Furthermore, by examining the alternative formulation, we can see exactly how to deal with the model comparison problem we introduced at the beginning of the chapter, where one analyst had reported performance statistics over a representative but unbalanced population, and another had used a class-balanced population. A common way of expressing expected profit is to factor out the probabilities of seeing each class, often referred to as the class priors. The class priors specify the likelihood of seeing positive and negative instances, respectively. In other words, they give the overall probability of a positive or negative instance, whereas before, we had the probability of a true positive, false positive, true negative, and false negative. Factoring out the class priors allows us to separate the influence of class imbalance from the fundamental predictive power of the model, as we will discuss in more detail in Chapter 8. A rule of basic probability is that the probability of two different events both occurring is equal to the probability of one of them occurring times the probability of the other occurring, if we know that the first occurs. Said another way, the probability of x and y both occurring is equivalent to the probability of y occurring times the probability of x occurring, given that y occurs. Using this rule, we can re-express our expected profit as equal to the probability of a positive times the quantity of the probability that a given positive is a true positive times the benefit of a true positive plus the probability that a given positive is a false positive times the benefit of a false positive. And now let's add on the same for negatives. The probability of a negative times the quantity of the probability that a given negative is a true negative times the benefit of a true negative plus the probability that a given negative is a false negative times the benefit of a false negative. Phew. From this mess, we now have one component corresponding to the expected profit from the positive examples, and another, the second one, corresponding to the expected profit from the negative examples. Each of these is weighted by the probability that we see that sort of example. So, if positive examples are very rare, their contribution to the overall expected profit will be correspondingly small. Returning to the targeted marketing example, what is the expected profit of the model learned? We can calculate it using this equation. I won't bore you with the math, but the expected value comes to $50.04. This expected value means that if we apply this model to a population of prospective customers and mail offers to those it classifies as positive, we can expect to make an average of about $50 profit per consumer. We now have one way to deal with our motivating example from the beginning of the chapter. Instead of computing accuracies for the competing models, we would compute expected values. Furthermore, using this alternative formulation, we can compare the two models even though one analyst tested using a representative distribution and the other tested using a class balance distribution. In each calculation, we simply can replace the priors. Warning: to close this section on estimated profit, we emphasize two pitfalls that are common when formulating cost-benefit matrices. 1. It is important to make sure the signs of quantities in the cost-benefit matrix are consistent. In this book, we take benefits to be positive and costs to be negative. In many data mining studies, the focus is on minimizing cost rather than maximizing profit, so the signs are reversed. Mathematically, there is no difference. However, it is important to pick one view and be consistent. 2. An easy mistake in formulating cost-benefit matrices is to double count by putting a benefit in one cell and a negative cost for the same thing in another cell, or vice versa. A useful practical test is to compute the benefit improvement for changing the decision on an example test instance. For example, say you've built a model to predict which accounts have been defrauded. You've determined that a fraud case costs $1,000 on average. If you decide that the benefit of catching fraud is therefore $1,000 per case on average, and the cost of missing fraud is negative $1,000 per case, then what would be the improvement in benefit for catching a case of fraud? You calculate $2,000, but intuitively, you know that this improvement should only be about $1,000. So, this error indicates double counting. The solution is to specify either that the benefit of catching fraud is $1,000 or that the cost of missing fraud is negative $1,000, but not both. One should be 0. Sidebar: Other evaluation metrics. There are many evaluation metrics you will likely encounter in data science. All of them are fundamentally summaries of the confusion matrix. True positive rate and false negative rate refer to the frequency of being correct and incorrect, respectively, when the instance is actually positive. The true negative rate and false positive rate are analogous for the instances that are actually negative. We will continue to explore these measures in Chapter 8. The metrics precision and recall are also often used, especially in text classification and information retrieval. Recall is the same as true positive rate, while precision is the accuracy over the cases predicted to be positive. Practitioners in many fields such as statistics, pattern recognition, and epidemiology speak of the sensitivity and specificity of a classifier. Really, specificity is the true positive rate, the same as recall, and sensitivity is the true negative rate. You may also hear about the positive prediction value, which is the same as precision. The last one I'll mention, accuracy, is simply the count of correct decisions divided by the total number of decisions. Just remember, you can always look these terms up. Evaluation, baseline performance, and implications for investments in data. Up to this point, we have talked about model evaluation in isolation. In some cases, just demonstrating that a model generates some non-zero profit or a positive return on investment will be informative by itself. Nevertheless, another fundamental notion in data science is it is important to consider carefully what would be a reasonable baseline against which to compare model performance. This is important for the data science team in order to understand whether they indeed are improving performance, and is equally important for demonstrating to stakeholders that mining the data has added value. So, what is an appropriate baseline for comparison? The answer, of course, depends on the actual application. And coming up with a suitable baseline is one task for the business understanding phase of the data mining process. However, there are some general principles that can be very helpful. For classification models, it is easy to simulate a completely random model and measure its performance. The visualization frameworks we will discuss in Chapter 8 have natural baselines showing what random classification should achieve. This is useful for very difficult problems or initial explorations. Comparison against a random model establishes that there is some information to be extracted from the data. However, beating a random model may be easy, or may seem easy, so demonstrating superiority to it may not be very interesting or informative. A data scientist will often need to implement an alternative model, usually one that is simple but not simplistic, in order to justify continuing the data mining effort. In Nate Silver's book on prediction, The Signal and the Noise, he mentions the baseline issue with respect to weather forecasting. There are two basic tests that any weather forecast must pass to demonstrate its merit. It must do better than what meteorologists call persistence, the assumption that the weather will be the same tomorrow and the next day as it was today. It must also beat climatology, the long-term historical average of conditions on a particular date in a particular area. In other words, weather forecasters have two simple, but not simplistic, baseline models that they compare against. One, persistence, predicts that the weather tomorrow is going to be whatever it was today. The other, climatology, predicts whatever the average historical weather has been on this day from prior years. Each model performs considerably better than random guessing, and both are so easy to compute that they make natural baselines of comparison. Any new, more complex model must beat these. What are some general guidelines for good baselines? For classification tasks, one good baseline is the majority classifier, a naive classifier that always chooses the majority class of the training dataset. This may seem like advice so obvious it can be passed over quickly, but it is worth spending an extra moment here. There are many cases where smart, analytical people have been tripped up in skipping over this basic comparison. For example, an analyst may see a classification accuracy of 94% from her classifier and conclude that it is doing fairly well, when in fact, only 6% of the instances are positive. So, the simple majority prediction classifier also would have an accuracy of 94%. Indeed, many beginning data science students are surprised to find that the models they build from the data simply predict everything to be of the majority class. Note that this may make sense if the modeling procedure is set up to build maximum accuracy models. it may be hard to beat 94% accuracy. The answer, of course, is to apply the central idea of this chapter. Consider carefully what is desired from the data mining results. Maximizing simple prediction accuracy is usually not an appropriate goal. If that's what our algorithm is doing, we're using the wrong algorithm. For regressions problems, we have a directly analogous baseline. Predict the average value over the population, usually the mean or median. In some applications, there are multiple simple averages that one may want to combine. For example, when evaluating recommendation systems that internally predict how many stars a particular customer would give to a particular movie, we have the average number of stars a movie gets across the population, how well liked it is, and the average number of stars a particular customer gives to movies, what that customer's overall bias is. A simple prediction based on these two may do substantially better than using one or the other in isolation. Moving beyond these simple baseline models, a slightly more complex alternative is a model that only considers a very small amount of feature information. For example, recall from Chapter 3 our very first example of a data mining procedure: finding informative variables. If we find the one variable that correlates best with the target, we can build a classification or regression model that uses just that variable, which gives another view of baseline performance. How well does a simple, conditional model perform? Conditional here means that it predicts differently based on, or conditioned on, the value of the feature or features. The overall population average is therefore sometimes called the unconditional average. One example of mining such single-feature predictive models from data is to use tree induction to build a decision stump, a decision tree with only one internal node, the root node. A tree limited to one internal node simply means that the tree induction selects the single most informative feature to make a decision. In a well-known paper in machine learning, Robert Holt showed that decision stumps often produce quite good baseline performance on many of the test datasets used in machine learning research. A decision stump is an example of the strategy of choosing the single most informative piece of information available and basing all decisions on it. In some cases, most of the leverage may be coming from a single feature, and this method assesses whether and to what extent that is the case. This idea can be extended to data sources and relates to our fundamental principle from Chapter 1 that we should regard data as an asset to be invested in. If you are considering building models that integrate data from various sources, you should compare the result to models built from the individual sources. Often, there are substantial costs to acquiring new sources of data. In some cases, these are actual monetary costs. In other cases, they involve commitments of personnel time for managing relationships with data providers and monitoring data feeds. To be thorough, for each data source, the data science team should compare a model that uses the source to one that does not. Such comparisons help to justify the cost of each source by quantifying its value. If the contribution is negligible, the team may be able to reduce costs by eliminating it. Beyond comparing simple models and reduced data models, it is often useful to implement simple, inexpensive models based on domain knowledge or received wisdom and evaluate their performance. For example, in one fraud detection application, it was commonly believed that most defrauded accounts would experience a sudden increase in usage, and so checking accounts for sudden jumps in volume was sufficient for catching a large proportion of fraud. Implementing this idea was straightforward, and it provided a useful baseline for demonstrating the benefit of data mining. This essentially was a single-feature predictive model. Similarly, an IBM team that used data mining to direct sales efforts chose to implement a simple sales model that prioritized existing customers by the size of previous revenue and other companies by annual sales. They were able to demonstrate that their data mining added significant value beyond this simpler strategy. Whatever the data mining group chooses as a baseline for comparison, it should be something the stakeholders find informative and hopefully persuasive. Summary. A vital part of data science is arranging for proper evaluation of models. This can be surprisingly difficult to get right and will often require multiple iterations. It is tempting to use simple measures, such as classification accuracy, since these are simple to calculate, are used in many research papers, and may be what one learned in school. However, in real-world domains, simplistic measures rarely capture what is actually important for the problem at hand, and often mislead. Instead, the data scientist should give careful thought to how the model will be used in practice and devise an appropriate metric. The expected value calculation is a good framework for organizing this thinking. It will help to frame the evaluation, and in the event that the final deployed model produces unacceptable results, it will help identify what is wrong. The characteristics of the data should be taken into account carefully when evaluating data science results. For example, real classification problems often present data with very unbalanced class distributions. That is, the classes will not occur with equal prevalence. Adjusting class proportions may be useful, or even necessary, to learn a model from the data. However, evaluation should use the original, realistic population so that the results reflect what will actually be achieved. To calculate the overall expected value of a model, the costs and benefits of decisions must be specified. If this is possible, the data scientist can calculate an expected cost per instance for each model and choose whichever model produces the lowest expected cost or greatest profit. It also is vital to consider what one should compare a data-driven model against, to judge whether it performs well or better. The answer to this question is intimately tied to the business understanding, but there are a variety of general best practices that data science teams should follow. We explored the ideas of this chapter with applications of the concepts presented in the chapters that preceded. The concepts are more general, of course, and relate to our very first fundamental concept. Data should be considered an asset, and we need to consider how to invest. We considered this point by discussing briefly that one not only can compare different models and different baselines, but also compare results with different data sources. Different data sources may have different associated costs, and careful evaluation may show which can be chosen to maximize the return on investment. As a final summary point, this chapter has discussed single quantitative numbers as summary estimates of model performance. They can answer questions like, how much profit can I expect to make? And should I use model A or model B? Such answers are useful, but provide only single-point values that hold under a specific set of assumptions. It is often revealing to visualize model behavior under a broad range of conditions. The next chapter discusses graphical views of model behavior that can do just this. Chapter 8. Visualizing Model Performance. The fundamental concepts discussed in this chapter are visualization of model performance under various kinds of uncertainty, and further consideration of what is desired from data mining results. The exemplary techniques are profit curves, cumulative response curves, lift curves, and rock curves. The previous chapter introduced basic issues of model evaluation and explored the question of what makes for a good model. We developed detailed calculations based on the expected value framework. That chapter was much more mathematical than previous ones, and if this is your first introduction to that material, you may have felt overwhelmed by the equations. Though they form the basis for what comes next, by themselves, they may not be very intuitive. In this chapter, we will take a different view to increase our understanding of what they are reviewing. The expected profit calculation in Chapter 7 takes a specific set of conditions and generates a single number, representing the expected profit in that scenario. Stakeholders outside of the data science team may have little patience for details and will often want a higher level, more intuitive view of model performance. Even data scientists who are comfortable with equations and dry calculations often find such single estimates to be impoverished and uninformative, because they rely on very stringent assumptions. For example, of precise knowledge of the costs and benefits, or that the model's estimates of probabilities are accurate. In short, it is often useful to present visualizations rather than just calculations, and this chapter presents some useful techniques. Ranking instead of classifying. Earlier, we discussed how the score assigned by a model can be used to compute a decision for each individual case based on its expected value. A different strategy for making decisions is to rank a set of cases by these scores, and then take actions on the cases at the top of the ranked list. Instead of deciding each case separately, we may decide to take the top n cases, or equivalently, all cases that score above a given threshold. There are several practical reasons for doing this. It may be that the model gives a score that ranks cases by their likelihood of belonging to the class of interest, but which is not a true probability. Recall our discussion in Chapter 4 of the distance from the separating boundary as a classifier score. More importantly, for some reason, we may not be able to obtain accurate probability estimates from the classifier. This happens, for example, in targeted marketing applications when one cannot get a sufficiently representative training sample. The classifier scores may still be very useful for deciding which prospects are better than others, even if a 1% probability estimate doesn't exactly correspond to a 1% probability of responding. A common situation is where you have a budget for actions, such as a fixed marketing budget for a campaign, and so you want to target the most promising candidates. If one is going to target the highest expected value cases using costs and benefits that are constant for each class, then ranking cases by likelihood of the target class is sufficient. There is no great need to care about the precise probability estimates. The only caveat is that the budget be small enough so that the actions do not go into negative expected value territory. For now, we will leave that as a business understanding task. It also may be that costs and benefits cannot be specified precisely, but nevertheless, we would like to take actions, and are happy to do so on the highest likelihood cases. We'll return to this situation in the next section. Note, if individual cases have different costs and benefits, then our expected value discussion in Chapter 7 should make it clear that simply ranking by likelihood will not be sufficient. When working with a classifier that gives scores to instances, in some situations, the classifier decisions should be very conservative, corresponding to the fact that the classifier should have high certainty before taking the positive action. This corresponds to using a high threshold on the output score. Conversely, in some situations, the classifier can be more permissive, which corresponds to lowering the threshold. This introduces a complication for which we need to extend our analytical framework for assessing and comparing models. Earlier, we stated that a classifier produces a confusion matrix. With a ranking classifier, a classifier plus a threshold produces a single confusion matrix. Whenever the threshold changes, the confusion matrix may change as well, because the numbers of true positives and false positives change. This leaves us with two questions. How do we compare different rankings? And how do we choose a proper threshold? If we have accurate probability estimates and a well-specified cost-benefit matrix, then we already answered the second question in our discussion of expected value. We determine the threshold where our expected profit is above a desired level, usually 0. Let's explore and extend this idea. Profit curves. We know how to compute expected profit, and we've just introduced the idea of using a model to rank instances. We can combine these ideas to construct various performance visualizations in the form of curves. Each curve is based on the idea of examining the effect of thresholding the value of a classifier at successive points, implicitly dividing the list of instances into many successive sets of predicted positive and negative instances. As we move the threshold down the ranking, we get additional instances predicted as being positive rather than negative. Each threshold, that is, each set of predicted positives and negatives, will have a corresponding confusion matrix. The previous chapter taught us that once we have a confusion matrix, along with knowledge of the cost and benefits of decisions, we can generate an expected value corresponding to that confusion matrix. More specifically, with a ranking classifier, we can produce a list of instances in their predicted scores, ranked by decreasing score, and then measure the expected profit that would result from choosing each successive cut point in the list. Conceptually, this amounts to ranking the list of instances by score from highest to lowest and sweeping down through it, recording the expected profit after each instance. At each cut point, we record the percentage of the list predicted as positive and the corresponding estimated profit. Graphing these values gives us a profit curve. Let's say we have a graph showing the profit curves of 3 classifiers. This graph is based on a test set of 1,000 consumers, say, a small random population of people to whom you test marketed earlier. Percentage of test instances is on the x-axis, and profit is on the y-axis. When interpreting results, we normally will talk about percentages of consumers so as to generalize to the population as a whole. For each curve, the consumers are ordered from highest to lowest probability of accepting an offer based on some model. For this example, let's assume our profit margin is small. Each offer costs $5 to make and market, and each accepted offer earns $9 for a profit of $4. Thus, according to the cost matrix, true positives will result in a benefit of $4, and false positives in a benefit of -$5, while true and false negatives have no cost or benefit. Profits can go negative. Not always, but sometimes they will, depending on the costs and the class ratio. In particular, this will happen when the profit margin is thin and the number of responders is small. The profit curves show you, going into the red, below the $0 profit line, by working too far down the list and making offers to too many people who won't respond, thereby spending too much on the costs of the offers. Note that all the profit curves on our graph begin and end at the same point. This should make sense, because at the left side, where no customers are targeted, there are no expenses and 0 profit. At the right side, where everyone is targeted, each of our classifiers performs the same. In between, there are some differences depending on how the classifiers order the customers. The random classifier performs worst because it has an even chance of choosing a responder or a non-responder. Classifier 2, on the other hand, produces the maximum profit of $200 by targeting the top-ranked 50% of consumers. If your goal was simply to maximize profit, and you had unlimited resources, you should choose Classifier 2. Use it to score your population of customers and target the top half, highest 50% of customers on the list. Now consider a slightly different but very common situation where you're constrained by a budget. You have a fixed amount of money available, and you must plan how to spend it before you see any profit. This is common in situations such as marketing campaigns. As before, you still want to target the highest ranked people, but now you have a budgetary constraint that may affect your strategy. Say you have 100,000 total customers and a budget of $40,000 for the marketing campaign. You want to use the modeling results, in this example, the profit curves, to figure out how best to spend your budget. What do? Well, first you figure out how many offers you can afford to make. Each offer costs $5, so you can target at most 8,000 customers, our $40,000 budget divided by 5. As before, you want to identify the customers most likely to respond, but each model ranks customers differently. Which model should you use for this campaign? 8,000 customers is 8% of your total customer base, so check the performance curves at x equals 8%. Our graph shows that the best performing model at this performance point isn't Classifier 2, but Classifier 1. You should use it to score the entire population, then send offers to the highest ranking 8,000 customers. In summary, from this scenario, we see that adding a budgetary constraint causes not only a change in the operating point, targeting 8% of the population instead of 50%, but also a change in the choice of classifier to do the ranking. Rock graphs and curves. Profit curves are appropriate when you know fairly certainly the conditions under which a classifier will be used, Specifically, there are two critical conditions underlying the profit calculation. One, the class priors, that is, the proportion of positive and negative instances in the target population, also known as the base rate, usually referring to the proportion of positives, which, as you know, impacts expected profit. 2. The costs and benefits. The expected profit is specifically sensitive to the relative levels of costs and benefits for the different cells of the cost-benefit matrix. If both class priors and cost-benefit estimates are known and are expected to be stable, profit curves may be a good choice for visualizing model performance. However, in many domains, these conditions are uncertain or unstable. In fraud detection domains, for example, the amount of fraud changes from place to place, and from one month to the next. The amount of fraud influences the priors. In the case of mobile phone churn management, marketing campaigns can have different budgets, and offers may have different costs, which will change the expected costs. One approach to handling uncertain conditions is to generate many different expected profit calculations for each model. This may not be very satisfactory. The sets of models, sets of class priors, and sets of decision costs multiply in complexity. This often leaves the analyst with a large stack of profit graphs that are difficult to manage, difficult to understand the implications of, and difficult to explain to a stakeholder. Another approach is to use a method that can accommodate uncertainty by showing the entire space of performance possibilities. One such method is the Receiver Operating Characteristics, ROC graph. A ROC graph is a two-dimensional plot of a classifier with false positive rate on the x-axis against true positive rate on the y-axis. As such, a ROC graph depicts relative trade-offs that a classifier makes between benefits, true positives, and costs, false positives. A discrete classifier is one that outputs only a class label, as opposed to a ranking. As already discussed, each such classifier produces a confusion matrix, which can be summarized by certain statistics regarding the numbers and rates of true positives, false positives, true negatives, and false negatives. Note that, although the confusion matrix contains 4 numbers, we really only need 2 of the rates, either the true positive rate or the false negative rate, and either the false positive rate or the true negative rate. Given one from either pair, the other can be derived since they sum to 1. Let's consider a ROC graph showing the performance of 3 discrete classifiers, A, B, and C. It is conventional to use the true positive rate and the false positive rate, and we will keep to that convention so the ROC graph will make sense. Each discrete classifier produces a false positive rate, true positive rate pair corresponding to a single point in ROC space. Importantly for what follows, the true positive rate is computed using only the actual positive examples, and the false positive rate is computed using only the actual negative examples. Note, remembering exactly what statistics the true positive and false positive rates refer to can be confusing for someone who does not deal with such things on a daily basis. It can be easier to remember by using less formal but more intuitive names for the statistics. The true positive rate is sometimes referred to as the hit rate, what percent of the actual positives the classifier gets right. The false positive rate is sometimes referred to as the false alarm rate, what percent of the actual negative examples the classifier gets wrong, that is, predicts to be positive. Several points in ROC space are important to note. The lower left point, 0, 0, represents the strategy of never issuing a positive classification. Such a classifier commits no false positive errors, but also gains no true positives. The opposite strategy of unconditionally issuing positive classifications is represented by the upper right point, 1, 1. The point 0, 1 represents perfect classification. The diagonal line connecting 0, 0 to 1, 1 represents the policy of guessing a class. For example, if a classifier randomly guesses the positive class half the time, it can be expected to get half the positives and half the negatives correct. This yields the point 0.5 in rock space. If it guesses the positive class 90% of the time, it can be expected to get 90% of the positives correct, but its false positive rate will increase to 90% as well, yielding 0.9 in rock space. Thus, a random classifier will produce a rock point that moves back and forth on the diagonal based on the frequency with which it guesses the positive class. In order to get away from this diagonal into the upper right triangle region, the classifier must exploit some information in the data. If classifier C's performance, for example, is 0.6, it is virtually random. C may be said to be guessing the positive class 60% of the time. Note that no classifier should be in the lower right triangle region of a rock graph. This represents performance that is worse than random guessing. One point in rock space is superior to another if it is the northwest of the first. Either its true positive rate is higher and false positive rate is no worse, or its false positive rate is lower and true positive rate is no worse. Or both are better. Classifiers appearing on the left-hand side of a rock graph, near the x-axis, may be thought of as conservative. They raise alarms, make positive classifications only with strong evidence, so they make few false positive errors, but they often have low true positive rates as well. Classifiers on the upper right-hand side of a rock graph may be thought of as permissive. They make positive classifications with weak evidence, so they classify nearly all positives correctly, but they often have high false positive rates. In our example, classifier A, at coordinates 0.2, 0.4, is more conservative than classifier B, at coordinates 0.4, 0.8. Many real-world domains are dominated by large numbers of negative instances, so performance in the far left-hand side of the rock graph is often more interesting than elsewhere. If there are many negative examples, even a moderate false alarm rate can be unmanageable. A ranking model produces a set of points, a curve, in rock space. As discussed previously, a ranking model can be used with a threshold to produce a discrete, binary classifier. If the classifier output is above the threshold, the classifier produces a Y. Otherwise, it produces an N. Each threshold value produces a different point in rock space. Conceptually, we may imagine sorting the instances by score and varying a threshold from negative infinity to infinity while tracing a curve through rock space. Whenever we pass a positive instance, we take a step upward, increasing true positives. Whenever we pass a negative instance, we take a step rightward, increasing false positives. Thus, the curve is actually a step function for a single test set, but with enough instances, it appears smooth. An advantage of rock graphs is that they decouple classifier performance from the conditions under which the classifiers will be used. Specifically, they are independent of the class proportions as well as the costs and benefits. A data scientist can plot the performance of classifiers on a rock graph as they are generated, knowing that the positions and relative performance of the classifiers will not change. The region, or regions, on the rock graph that are of interest may change as costs, benefits, and class proportions change, but the curves themselves should not. Both Stein and Provost and Fawcett show how the operating conditions of the classifier, the class priors and error costs, can be combined to identify the region of interest on its rock curve. Briefly, knowledge about the range of possible class priors can be combined with knowledge about the cost and benefits of decisions. Together, these describe a family of tangent lines that can identify which classifier, or classifiers, should be used under those conditions. Stein presents an example from finance, loan defaulting, and shows how this technique can be used to choose models. The area under the rock curve. An important summary statistic is the area under the rock curve, AUC. As the name implies, this is simply the area under a classifier's curve expressed as a fraction of the unit square. Its value ranges from 0 to 1. Though a ROC curve provides more information than its area, the AUC is useful when a single number is needed to summarize performance, or when nothing is known about the operating conditions. Later in the chapter, we will discuss a use of the AUC statistic. For now, it is enough to realize that it's a good general summary statistic of the predictiveness of a classifier. Tip: as a technical note, the AUC is equivalent to the Mann-Whitney-Wilcoxon measure, a well-known ordering measure in statistics. It is also equivalent to the Gini coefficient, with a minor algebraic transformation. Both are equivalent to the probability that a randomly chosen positive instance will be ranked ahead of a randomly chosen negative instance. Cumulative response and lift curves. ROC curves are a common tool for visualizing model performance for classification, class probability estimation, and scoring. However, as you may have just experienced if you are new to all this, ROC curves are not the most intuitive visualization for many business stakeholders who really ought to understand the results. It is important for the data scientist to realize that clear communication with key stakeholders is not only a primary goal of her job, but also is essential for doing the right modeling, in addition to doing the modeling right. Therefore, it can be useful also to consider visualization frameworks that might not have all the nice properties of ROC curves, but are more intuitive. It is important for the business stakeholder to realize that the theoretical properties that are sacrificed sometimes are important, so it may be necessary in certain circumstances to pull out the more complex visualizations. One of the most common examples of the use of an alternative visualization is the use of the cumulative response curve, rather than the ROC curve. They are closely related, but the cumulative response curve is more intuitive. Cumulative response curves plot the true positive rate, the percentage of positives correctly classified, on the y-axis, as a function of the percentage of the population that is targeted on the x-axis. So, conceptually, as we move down the list of instances ranked by the model, we target increasingly larger proportions of all the instances. Hopefully in the process, if the model is any good, when we are at the top of the list, we will target a larger proportion of the actual positives than actual negatives. As with ROC curves, the diagonal line x equals y represents random performance. In this case, the intuition is clear. If you target 20% of all instances completely randomly, you should target 20% of the positives as well. Any classifier above the diagonal is providing some advantage. Note: the cumulative response curve is sometimes called a lift curve, because one can see the increase over simply targeting randomly as how much the line representing the model performance is lifted up over the random performance diagonal. We will call these curves cumulative response curves because lift curve also refers to a curve that specifically plots the numeric lift. Intuitively, the lift of a classifier represents the advantage it provides over random guessing. The lift is the degree to which it pushes up the positive instances in a list above the negative instances. For example, consider a list of 100 customers, half of whom churn, positive instances, and half who do not, negative instances. If you scan down the list and stop halfway, representing 50% targeted, how many positives would you expect to have seen in the first half? If the list were sorted randomly, you would expect to have seen only half the positives, giving a lift of 50% divided by 50%, or 1. If the list had been ordered by an effective ranking classifier, more than half the positives should appear in the top half of the list, producing a lift greater than 1. If the classifier were perfect, all positives would be ranked at the top of the list, so by the midway point, we would have seen 100% of them, giving a lift of 100% divided by 50%, or 2. The lift curve is essentially the value of the cumulative response curve at a given x point, divided by the diagonal line, y equals x, value at that point. The diagonal line of a cumulative response curve becomes a horizontal line at y equals 1 on the lift curve. Sometimes you will hear claims like, our model gives a 2 times lift. This means that at the chosen threshold, often not mentioned, the lift curve shows that the model's targeting is twice as good as random. On the cumulative response curve, the corresponding true positive rate for the model will be twice the true positive rate for the random performance diagonal. You might also compute a version of lift with respect to some other baseline. The lift curve plots this numeric lift on the y-axis against the percent of the population targeted on the x-axis, the same x-axis as the cumulative response curve. Both lift curves and cumulative response curves must be used with care if the exact proportion of positives in the population is unknown or is not represented accurately in the test data. Unlike for ROC curves, these curves assume that the test set has exactly the same target class priors as the population to which the model will be applied. This is one of the simplifying assumptions that we mentioned at the outset that can allow us to use a more intuitive visualization. As an example, in online advertising, the base rate of observed response to an advertisement may be very small. 1 in 10 million is not unusual. Modelers may not want to have to manage datasets that have 10 million non-responders for every responder, so they downsample the non-responders and create a more balanced dataset for modeling and evaluation. When visualizing classifier performance with ROC curves, this will have no effect, because, as mentioned earlier, the axes each correspond only to the proportions of one class. However, lift and cumulative response curves will be different. The basic shapes of the curves may still be informative, but the relationships between the values on the axes will not be valid. Example: performance analytics for churn modeling. The last few chapters have covered a lot of territory in evaluation. We've introduced several important methods and issues in evaluating models. In this section, we tie them together with a single application case study to show the results of different evaluation methods. The example we'll use is our ongoing domain of cell phone churn. However, in this section, we use a different and more difficult churn dataset than was used in previous chapters. It is a dataset from the 2009 KDD Cup data mining competition. We did not use this dataset in earlier examples because these attribute names and values have been anonymized extensively to preserve customer privacy. This leaves very little meaning in the attributes and their values, which would have interfered with our discussions. However, we can demonstrate the model performance analytics with the sanitized data. From the website, the KDD Cup 2009 offers the opportunity to work on large marketing databases from the French telecom company Orange to predict the propensity of customers to switch provider, churn, buy new products or services, appetency, or buy upgrades or add-ons proposed to them to make the sale more profitable, upselling. The most practical way in a CRM system to build knowledge on customer is to produce scores. A score, the output of a model, is an evaluation for all instances of a target variable to explain, that is, churn, appetency, or upselling. Tools which produce scores allow to project, on a given population, quantifiable information. The score is computed using input variables which describe instances. Scores are then used by the information system, for example, to personalize the customer relationship. Little of the dataset is worth describing because it has been thoroughly sanitized, but its class skew is worth mentioning. There are about 47,000 instances altogether, of which about 7% are marked as churn, positive examples, and the remaining 93% are not, negatives. This is not severe skew, but it's worth noting for reasons that will become clear. We emphasize that the intention is not to propose good solutions for this problem or to suggest which models might work well, but simply to use the domain as a testbed to illustrate the ideas about evaluation we've been developing. Little effort has been done to tune performance. We will train and test several models: a classification tree, a logistic regression equation, and a nearest neighbor model. We will also use a simple Bayesian classifier called naive Bayes, not discussed until Chapter 9. For the purpose of this section, details of the models are unimportant. All the models are black boxes, with different performance characteristics. We're using the evaluation and visualization techniques introduced in the last chapters to understand their characteristics. Let's begin with a very naive evaluation. We'll train on the complete dataset and then test on the same dataset we're trained on. We'll also measure simple classification accuracies. The accuracy values of our 4 classifiers trained and tested on the complete KDD Cup 2009 churn problem are 95% for the classification tree, 93% for logistic regression, 100% for k-nearest neighbor, and 76% for naive Bayes. Several things are striking here. First, there appears to be a wide range of performance, from 76% to 100%. Also, since the dataset has a base rate of 93%, any classifier should be able to achieve at least this minimum accuracy. This makes the naive Bayes result look strange since it's significantly worse. Also, at 100% accuracy, the k-nearest neighbor classifier looks suspiciously good. But this test was performed on the training set, and by now, having listened to Chapter 5, you realize such numbers are unreliable, if not completely meaningless. They are more likely to be an indication of how well each classifier can memorize, overfit, the training set than anything else. So, instead of investigating these numbers further, let's redo the evaluation properly using separate training and test sets. We could just split the dataset in half, but instead, we'll use the cross-validation procedure discussed in Chapter 5. This will not only ensure proper separation of datasets, but also provide a measure of variation in our results. Each accuracy number is an average of 10-fold cross-validation, followed by the standard deviation of the measurements. Including a standard deviation may be regarded as a kind of sanity check. A large standard deviation indicates the test results are very erratic, which could be the source of various problems, such as the dataset being too small, or the model being a very poor match to a portion of the problem. Using cross-validation, we find that the accuracy of the classification tree is 91.8% with a standard deviation of 0. Logistic regression has an accuracy of 93% with a standard deviation of 0.1. K-nearest neighbor has an accuracy of 93% with a standard deviation of 0. And naive Bayes has an accuracy of 76.5% with a standard deviation of 0.6. The accuracy numbers have all dropped considerably, except for naive Bayes, which is still oddly low. The standard deviations are fairly small compared to the means, so there is not a great deal of variation in the performance on the folds. This is good. We also have values for the area under the ROC curve, commonly abbreviated AUC. We briefly discussed this AUC measure earlier, noting it as a good general summary statistic of the predictiveness of a classifier. It varies from 0 to 1. A value of 0.5 corresponds to randomness, meaning the classifier cannot distinguish at all between positives and negatives, and a value of 1 means that it is perfect in distinguishing them. One of the reasons accuracy is a poor metric is that it is misleading when datasets are skewed, which this dataset is, with 93% negatives and 7% positives. All 4 of our models here have an AUC between 0.5 and 0.65, indicating that they're somewhat better than random predictions, but nowhere near perfect. Recall that we introduced fitting curves earlier as a way to detect when a model is overfitting. The idea is that as a model is allowed to get more and more complex, it typically fits the data more and more closely. But at some point, it is simply memorizing the idiosyncrasies of the particular training set rather than learning the general characteristics of the population. A fitting curve plots model complexity against a performance measure using 2 datasets, the set it was trained upon and a separate holdout set. Consider the fitting curves for our classification tree model, which plot the number of nodes in the tree against the AUC. When performance on the holdout set starts to decrease, overfitting is occurring. And in this case, we find that the classification tree definitely is overfitting, and the other models probably are too. The sweet spot, where holdout performance is maximum, is at about 100 tree nodes, beyond which the performance on the holdout data declines.